These are the answers to homework 2C. Here are the definitions I'd like you to know. Now, on to the questions. Number 1, calculate the volume of oxygen gas that can be produced at 30 degrees Celsius and 725 torr from the complete decomposition of 4.10 grams of mercury 2 oxide. First, the balanced equation. The decomposition of mercury 2 oxide will turn into elemental mercury and elemental oxygen, which is diatomic. To balance the oxygens, a 2 in front of the mercury 2 oxide. To balance the mercury, 2 in front of mercury. Given information in the problem, 4.10 grams of mercury 2 oxide are being decomposed. The question is, how many liters of oxygen gas will be produced? From the balanced equation, the significant mole ratio is 2 moles of mercury 2 oxide always produce 1 mole of diatomic oxygen. First step in a stoichiometric calculation is to convert given information into moles, and we can convert the 4.10 grams of mercury 2 oxide into moles. The molar mass of mercury 2 oxide will be the sum of 1 mole of mercury, 200.6 grams per mole, and 1 mole of oxygen, 16.00 grams per mole, giving 216.6 grams per mole. Now, there's a 2 in front of the mercury 2 oxide in the balanced equation. Sometimes people think you need to multiply the molar mass by 2, but that can't be true. It's not going to be 433.2 grams of mercury 2 oxide per 1 mole, and it's not going to be 216.6 grams of mercury 2 oxide per 2 moles of HGO. When you calculate it, you're calculating how many grams it takes for 1 mole of HGO. So in case you're ever tempted to multiply the molar mass by 2, or in this fraction here, put a 2 moles on the top over 216.6, that would be incorrect. Molar masses are determined independently from the balanced equation. Don't use a coefficient in front to convert or calculate your molar mass. So 1 mole of HGO weighs 216.6 grams, arranged with the grams on the bottom to cancel out, and this will determine the moles of mercury 2 oxide. Second will be the mole ratio in the balanced equation. It's 2 moles of HGO on the bottom, 1 mole of O2 on the top to cancel out. And the final step is always converting moles into the units they want. In this case, they want liters of oxygen, so we're not going to be able to do this by a simple conversion factor. We're going to have to use PV equals nRT to convert moles of oxygen into liters of oxygen. Because this is a gas volume, I'm going to calculate, therefore, the moles of oxygen at this point in the calculation. And then I'm going to go to PV equals nRT, and I'm going to solve it for V. And we'll plug in all the relevant data for oxygen. They've told us that we've calculated the moles of oxygen to be 0.00946 with a guard digit 4. We'll use the universal gas constant, 0.08206 liter atmospheres per mole Kelvin. We'll take the 30 degrees Celsius and convert that into Kelvin, and that's 303 with a guard digit 0.2. And the given pressure of 725 torr needs to be divided by 760 to convert it into atmospheres, which turns out to be 0.953 guard digit 9 atmospheres. Moles cancel out, atmospheres cancel out, Kelvin cancel out, and we're left over with liters. And so we will have calculated that if you decompose 4.10 grams of mercury 2 oxide, you will produce 0.247 liters of oxygen gas. Question number 2. Urea is used as a nitrogen source in fertilizers and can be produced commercially from the reaction of ammonia and carbon dioxide given here. Calculate the mass of urea that can be produced if 500 liters of ammonia at 223 degrees Celsius and 90 atmospheres are reacted with 600 liters of carbon dioxide at 223 degrees Celsius and 45 atmospheres. The given information in the problem, 500 liters of the reactant ammonia, 600 liters of the reactant carbon dioxide. The question is, how many grams of urea will be produced? Because we're given 2 different amounts of 2 different reactants, we don't know which one is going to be completely used up in this chemical reaction, i.e. which one will be the limiting reactant. So we're going to have to do an ICF table for this and calculate which of the 2 reactants are actually used up. The initial, change, and final table is based on moles, so I'm going to convert the 500 liters of ammonia into moles, the 600 liters of carbon dioxide into moles, and then create the ICF table, where the important relationship is going to be the coefficients in the balanced equation. 2 moles of ammonia react with 1 mole of carbon dioxide to produce 1 mole of urea. So to calculate the moles of ammonia, I will use the ideal gas law equation. The given pressure was 90 atmospheres. The volume was 500 liters. We'll use the universal gas constant, and the temperature 223 degrees Celsius, switched to Kelvin, 496 with a guard digit 0.2 Kelvin. Atmospheres, liters, and Kelvin cancel out. The mole in the denominator under a fraction bar flips to the top, and we wind up getting a 2 significant figure number of 1,100 moles of ammonia. With guard digits, it would be 1,105. Same thing for the carbon dioxide. Its pressure, 45 atmospheres, its volume, 600 liters, and the temperature, 496.2. When we cancel out the units, we'll once again have moles flipping to the top, and to 2 significant figures, we'll have 660 moles of carbon dioxide, or with the guard digit 663. So once you know the moles of each of the reactants in a limiting reactant problem, we're going to now write the initial moles down for each substance: 1,105 moles of ammonia, 663 moles of carbon dioxide, and then the one product we're interested in, the urea, there's actually none of it to start. So we have to determine which of the 2 reactants gets used up completely, and it's either the ammonia or the carbon dioxide. You essentially have to guess which it is. Sometimes the numbers are easy enough to tell. For example, if we start with 1,100 moles of ammonia and it's a 2-to-1 ratio to carbon dioxide, we would probably only use about 550 moles of carbon dioxide, which means you'd have some carbon dioxide left over. The ammonia is probably the limiting reactant. However, if you were going to start with, let's say, 600 moles of carbon dioxide, you would have to use 1,200 moles of ammonia, which is greater than the 1,105 given. So carbon dioxide can't be the limiting reactant. But if the numbers are more challenging and you can't do that in your head, just pick one randomly. Let's say we're going to assume 1,100 moles of ammonia are the limiting reactant. Then with the coefficients in the balanced equation giving us the mole ratio of 2 moles of ammonia to 1 mole of carbon dioxide, I can multiply by that mole ratio to make the moles of ammonia cancel out, and I will calculate how much carbon dioxide will react with it, and it comes out 552.5, which is less than the 663. So that means if all the ammonia reacts away, I'm going to use a smaller amount of carbon dioxide that's present, so there'll be some left over. I've selected the correct limiting reactant, and that means all 1,105 moles of ammonia will react away, and it'll react with 552.5 moles of carbon dioxide. And because the carbon dioxide and the urea are in a 1-to-1 ratio, I will form 552.5 moles of urea. That answer there is actually a 2 significant figure number from our calculation at the bottom. Starting with 1,100 moles of ammonia, we've technically calculated 550 moles of carbon dioxide would react, so 550 moles of ammonia of urea would be formed. If we add up the columns, no ammonia left over, we have 110 moles of carbon dioxide left over, and to 2 significant figures, 550 moles of urea created. So we now know how many moles of urea have been produced. If we determine urea's molar mass, we can convert the moles into grams by multiplying it by its molar mass of 60.07 grams per mole, and we get an answer to 2 significant figures of 33,000 grams of urea produced from this reaction. Number 3, when a flask is charged with 0.265 grams of ammonia gas and 0.720 grams of nitrogen gas, the pressure was measured to be 4.43 atmospheres. A, draw the Lewis structure and bond orbital models for the molecules of each gas. First, for ammonia. Ammonia would have a total of 8 valence electrons, 5 from the hydrogen, 5 from the nitrogen, 3 from each of the hydrogens. Drawing a skeletal structure to bond the 3 hydrogens to it, we would use up 6 of the electrons. We need to add 2 more, and they will go in as a lone pair on the only atom that can have an octet. Hydrogens only get duets. The lone pair would go here. Octet for nitrogen, duets for hydrogen. This is the correct Lewis structure. To draw a bond orbital model, we'll determine the steric number of the nitrogen, which is 1, 2, 3, 4. Atoms with steric numbers of 4 form sp3 hybrid orbitals. sp3 hybrid orbitals point to the four corners of a tetrahedron. So we'll draw the four sp3 orbitals on the nitrogen as a tetrahedron, and three of those will have hydrogens bonded to them, and one of them will hold the lone pair. Each of the bonds in this molecule is the overlap of an sp3 orbital from the nitrogen and a 1s orbital from the hydrogen, so the bonds are all called sigma 1s plus sp3. For the nitrogen gas molecule, which is diatomic, nitrogen atoms have 5 valence electrons each, so 5 and 5 is 10. Here's our skeletal structure using 2 electrons to put the remaining electrons in. We already have 2, 4, 6, 8, and there's 10. This gives an octet to the left nitrogen, but there's no octet for the right nitrogen. So we have to move a lone pair into a sharing position to make a double bond, which still does not make an octet. So we'll move another lone pair into a sharing position to make another bond, a triple bond now in this case, and now both atoms have complete outer shells. To draw the bond orbital model, we need the steric number of each atom. And in this case, each atom has a steric number of 2. A bonded atom and a lone pair, 1 plus 1 is 2. With steric number of 2, the hybridization is sp. sp orbitals are linear, so I'm going to draw each nitrogen with a pair of linear sp orbitals. And then perpendicular to those sp orbitals will be a 2p orbital on the y-axis, then a 2p orbital on the z-axis. So pointing to the left and to the right are the sp hybrid orbitals. Pointing up and down would be a pz orbital, and pointing out towards you and going back would be a py orbital. The second nitrogen is exactly the same, so they use sp orbitals to point at each other, overlap, and make a single bond. The p orbitals are on the plane of the paper will overlap to make a pi bond, that's the second bond, and the p orbitals that are in front and behind the paper will overlap in front and behind to make another pi bond, that's the third bond, and the lone pairs go in the remaining sp orbitals. There are 2 types of bonds here, bond A and bond B. I'll name them separately. Bond A is a sigma sp plus sp, and the bond B's are just going to call generically pi 2p plus 2p. Part B, find the partial pressure of each gas in this mixture. Partial pressures are proportional to the mole fraction of each gas, and they told us the masses of each gas found in this particular flask, so we're going to have to convert the masses into moles. So the 0.265 grams of ammonia will use its molar mass to convert grams of ammonia into moles of ammonia. And the 3 significant figures, this comes out 0.0156 moles of ammonia. We'll do the same thing for the diatomic nitrogen. And because 1 mole of diatomic nitrogen has 2 moles of nitrogen in it, its molar mass is 28.02 grams per mole. This comes out 0.0257 moles. So to calculate the partial pressure of each gas, we'll need to do their mole fractions and multiply them by the total pressure of the gas mixture. So for the partial pressure of ammonia, the mole fraction is 0.01555 moles of ammonia divided by the total, and then that gets multiplied by the total pressure of 4.43 atmospheres. And this comes out 1.67 atmospheres of ammonia. The partial pressure of nitrogen will be its mole fraction, 0.0257, divided by the total, multiplied by the total pressure of 4.43 atmospheres, and that comes out to be 2.76 atmospheres as the partial pressure of the diatomic nitrogen.